1,800 feet. That's the distance between where the Greg Biffle citation impacted and where the runway threshold began. 1,800 feet is barely more than a quarter mile. It's 6 football fields. It's the length of 6 city blocks. In aviation terms, it's nothing. It's a distance that a jet on approach covers in about 10 seconds. But those 1,800 feet represent the difference between a successful emergency landing and a tragedy that claims 7 lives. Today, we need to talk about what happens in those final moments of an approach, why aircraft end up short of runways, and what the specific circumstances at Statesville Regional Airport tell us about the challenges the crew was facing. Because this isn't just about distance. It's about energy, terrain, visual references, and how quickly a situation can deteriorate when you're low, slow, and running out of options. And what we're going to discover is that 1,800 feet short isn't a random number. It's the signature of a very specific type of accident scenario, one that's been studied extensively and one that continues to claim lives despite decades of safety improvements. Let's start with the facts as we know them from the NTSB's initial briefings and publicly available data. The citation departed runway 10 at Statesville Regional Airport at approximately 10:05 a.m. on December 18th. After about 10 minutes of flight covering roughly 26 miles, the aircraft returned to attempt a landing on runway 28, which is the same runway approached from the opposite direction. Weather was marginal VFR with broken clouds at 1,200 feet, visibility around 5 miles, and light drizzle. The aircraft impacted terrain, trees, and airport lighting structures approximately 1,800 feet short of the runway 28 threshold. It struck multiple approach lights, severed them from their foundations, continued through trees and vegetation, breached the airport perimeter fence, and came to rest on the runway surface where it was consumed by fire. All 7 occupants were killed on impact. 1,800 feet short. That number tells us several critical things about what was happening in those final moments. First, it tells us the aircraft was on an approach to the runway. It wasn't wildly off course. It wasn't lost. It wasn't confused about where the airport was. The crew knew where the runway was, and they were trying to get to it. The flight path was aligned with the runway's center line. They were pointed in the right direction. But they were too low. They didn't have enough altitude to clear the obstacles and terrain between their position and the runway threshold. Second, 1,800 feet short tells us this wasn't a controlled flight into terrain in the classic sense. The crew wasn't flying along oblivious to their altitude. They knew they were low. They were trying to reach the runway. They just didn't have enough energy, enough altitude, enough performance to make it those final 1,800 feet. Now, let's talk about what 1,800 feet short means in terms of the approach profile. When you're flying a stabilized instrument approach, you follow a specific glide path, typically 3 degrees, that brings you down from the final approach fix to the runway threshold. A 3-degree glide path means you're descending at a rate of approximately 300 feet per nautical mile. So if you're 3 miles from the runway, you should be at about 900 feet above the runway elevation. If you're 2 miles out, you should be at 600 feet. If you're 1 mile out, you should be at 300 feet. Those numbers give you obstacle clearance and ensure you arrive at the runway threshold at the proper height, typically 50 feet above the ground, which is the standard threshold crossing height. But here's the thing. Statesville Regional Airport doesn't have a precision instrument approach with electronic glide slope guidance. It has non-precision approaches, which means pilots have to manage their own descent rate and glide path. There's no glide slope needle to follow. You're using altitude checkpoints and visual references to judge whether you're on the right path. That requires more skill, more attention, and more precise flying than a precision approach. And in marginal weather with low clouds and reduced visibility, managing a non-precision approach while dealing with an emergency is incredibly challenging. Now, 1,800 feet is roughly 3/10 of a mile. If we're talking about a 3-degree glide path, at 3/10 of a mile from the runway, an aircraft should be at about 90 feet above the runway elevation. That's the altitude you'd expect to be at if you're on a normal glide path at that distance. But the citation wasn't at 90 feet when it was 1,800 feet from the threshold. It was at ground level. It was impacting obstacles, which means the aircraft's glide path was significantly shallower than 3 degrees. The aircraft was dragging in, as pilots say. It was low on energy, descending at a rate it couldn't arrest. And despite the crew's best efforts, it couldn't climb or even maintain altitude to clear the obstacles. Let's talk about those obstacles, because terrain and obstacles in the approach path are critical factors in understanding why this accident happened where it did. Statesville Regional Airport sits at an elevation of 974 feet above sea level. That's not particularly high, but it's also not at sea level. The airport is located in the rolling Piedmont terrain of North Carolina, and the elevation of the surrounding area varies significantly. When you're approaching runway 28 from the southeast, you're flying over terrain that slopes upward toward the airport. The airport sits on slightly elevated ground compared to the approach path. That rising terrain creates a situation where you need to maintain a proper glide path to ensure obstacle clearance. According to the airport's instrument approach charts, there are trees and other obstacles in the approach corridor to runway 28. The approach lighting system, which is designed to give pilots visual guidance during the final stages of an approach, extends outward from the runway threshold. Those approach lights are mounted on poles and sit well above the ground level. The citation struck multiple approach lights, which tells us the aircraft was high enough to hit structures that are elevated above the terrain, but not high enough to clear them. Think about what that means. The approach lights might be 15 or 20 feet tall. The aircraft hit them, which means it was at that height when it reached that position. That's far too low for an aircraft that's still 1,800 feet from the runway. Here's where the terrain factor becomes really important. Several aviation analysts have noted that the approach to runway 28 at Statesville involves rising terrain. You're essentially flying toward a runway that sits on elevated ground. If you're already low on energy, if you're descending and can't arrest that descent, the rising terrain closes the gap between your aircraft and the ground even faster. It's like the ground is coming up to meet you. Even if your descent rate is constant, the rising terrain means you have less and less clearance. And if your aircraft is already in a descent it can't stop, that rising terrain guarantees you're going to hit something before you reach the runway. This is a phenomenon that's been studied extensively in aviation safety. It's sometimes called a black hole approach, though that term usually refers to night approaches over water or unlighted terrain. The concept is similar. When you're approaching a runway and you can't see the terrain clearly, when your visual references are limited, it's very easy to end up below a safe glide path. Your eyes deceive you. The runway looks like it's in the right place, but you're actually low. And by the time you realize you're low, you don't have enough altitude or energy to correct. In this case, the weather was a significant factor in limiting visual references. 1,200-foot ceilings and 5 miles visibility in drizzle means you're in and out of clouds. You can see the ground, but not clearly. Everything is gray and indistinct. Depth perception is compromised. It's difficult to judge your height above the ground accurately. And if you're also dealing with the stress of an emergency, if you're task saturated trying to manage a failed engine or other aircraft problems, your ability to accurately assess your glide path is further degraded. You think you're on the right path, but you're actually below it, and you don't realize it until it's too late. Let's talk about energy management, because this is absolutely central to understanding why the aircraft ended up 1,800 feet short. An aircraft's energy state is the combination of its altitude and its airspeed. Altitude is potential energy. Airspeed is kinetic energy. When you're high and fast, you have lots of energy. You can trade altitude for airspeed or airspeed for altitude. You have options. But when you're low and slow, your energy state is critical. You have very little margin. Every decision you make affects your energy. And once you've given up energy, it's very difficult to get it back, especially if your thrust is limited due to an engine failure. In the case of the Biffle citation, we know from the NTSB data that the aircraft was operating at relatively low altitude throughout the return to the airport. It never climbed above 3,000 or 4,000 feet, and for much of the approach, it was below 2,000 feet. We also know that the aircraft's airspeed varied, but there are indications it may have been on the slow side, especially if the crew had extended landing gear and flaps. Every configuration change that adds drag reduces your energy. Landing gear creates massive drag. Flaps create drag. If you extend them while you're still several miles from the runway, while you're still trying to maneuver into position, you're bleeding energy the entire time. And if your engine thrust is reduced because you've lost one engine or because both engines are damaged, you may not be able to maintain altitude with that much drag. Here's a scenario that fits the available data. The aircraft had some kind of emergency, possibly an engine failure, possibly related to an open baggage door and foreign object damage to an engine. The crew decided to return to Statesville. They flew past the airport and set up for an approach to runway 28. At some point, probably while they were still a few miles from the runway, they extended the landing gear and flaps to configure for landing. That configuration dramatically increased drag. The aircraft, already struggling with reduced thrust, couldn't maintain altitude. It began to descend. The crew added power, pulled back on the yoke, did everything they could to arrest the descent, but the aircraft simply didn't have enough performance. The descent continued. They were getting closer to the runway, but they were also getting lower and lower. The terrain was rising up toward the airport. Obstacles appeared in their path. They tried to clear them, but there wasn't enough energy. The aircraft struck the approach lights, plowed through trees, hit the fence, and crashed onto the runway. That scenario is consistent with what's called a high sink rate approach. The aircraft is configured for landing, but it's descending faster than normal. A normal descent rate on final approach is around 500 to 700 feet per minute. That gives you a stable, controlled descent that brings you to the runway at the right point. But if your descent rate is 1,000 feet per minute, or 1,200, or 1,500, you're coming down much faster than normal. And if you can't reduce that descent rate, if you don't have the thrust to arrest it, you're going to arrive at the ground before you arrive at the runway. The math is unforgiving. If you're descending at 1,200 feet per minute and you're at 300 feet altitude, you have 15 seconds before you hit the ground. 15 seconds. That's how quickly these situations develop. There's another factor that's worth discussing, and that's the difference between being configured for landing and having the energy to actually land. You can have your gear down and your flaps extended. You can be pointed at the runway. You can be doing everything by the book in terms of configuration. But if you don't have the energy, if you're too low and too slow, configuration doesn't matter. The aircraft is going to do what physics dictates. It's going to descend at a rate determined by your weight, your thrust, and your drag. And no amount of pilot input can change that if you're already at the limits of the aircraft's performance. Several Citation pilots have commented that the Citation 550 has limited performance on one engine, especially at heavy weight. The aircraft's single-engine service ceiling is significantly lower than its two-engine ceiling. If you're heavy, if you're configured with gear and flaps, if you've lost one engine, your ability to climb or even maintain altitude is severely limited. You might be able to hold altitude if you're clean, gear up, flaps up, flying at the optimum single-engine speed, but if you're dirty, configured for landing, you may not be able to hold altitude at all. You'll descend and there's nothing you can do about it except get the aircraft on the ground as quickly as possible. This is where the crew's decision-making comes into play. When should you extend the landing gear? When should you extend flaps? The answer depends on your energy state and your distance from the runway. If you're high and fast with plenty of margin, you can extend early. It helps you slow down and descend. But if you're low and slow, if your energy state is already marginal, extending gear and flaps early can be fatal. It locks you into a descent you can't escape from. The proper procedure, the procedure that's taught in training, is to delay configuration until you're stabilized on final approach and you're certain you have the energy to reach the runway. Don't configure early. Don't give up energy until you're sure you can spare it. But in an emergency, that discipline can break down. The crew is stressed, they're task saturated, they want to be ready to land, they see the airport, they think they're close enough, so they extend the gear, they extend the flaps, and suddenly they're descending faster than they expected. They add power, but it's not enough. They're committed to the descent and they can't stop it. That's a scenario that's been repeated in accident after accident. Premature configuration, energy bleed, high sink rate, impact short of the runway. It's a well-documented accident sequence, and it's one of the reasons why stabilized approach criteria are so heavily emphasized in modern pilot training. Let's talk about stabilized approach criteria, because this is a concept that might have saved this flight if it had been applied. The idea of a stabilized approach is simple. By the time you reach a certain point on final approach, usually 1,000 feet above the ground or 500 feet above the ground, depending on the type of operation, your aircraft should be in a stable configuration. You should be on speed, on glide path, on center line, with the proper configuration set, with thrust properly adjusted, with a normal descent rate. If you're not stabilized by that point, the procedure is to go around. Don't continue. Don't try to salvage the approach. Go around, climb back to a safe altitude, and set up for another attempt. The reason for this procedure is that unstabilized approaches are dangerous. If you're too fast, too slow, too high, too low, not configured properly, you're much more likely to have an accident. The statistics are overwhelming. The vast majority of approach and landing accidents involve unstabilized approaches. So the industry has adopted stabilized approach criteria as a standard. If you're not stable by the gate, go around. No exceptions. No trying to fix it in the last few hundred feet. Just go around. But here's the problem. That procedure assumes you have the aircraft performance to go around. It assumes you can apply power, pitch up, retract flaps and gear, and climb away. If your aircraft can't do that, if you've already lost an engine, or if you're so low on energy that you don't have climb capability, then going around isn't an option. You're committed to landing, whether you're stabilized or not. And if you're not stabilized, if you're high sink rate, below glide path, low on energy, your chances of making it to the runway are slim. This is one of the most difficult aspects of emergency flying. In a normal approach, if things aren't looking right, you go around. It's an easy decision. But in an emergency approach, especially if you've lost an engine or you're dealing with other performance limitations, going around might not be possible. You've got one shot. You have to make it work. And if your energy state is already marginal when you commit to the approach, you may not have enough margin to reach the runway. The crew of the Biffle flight may have been in exactly that situation. They knew they needed to land. They were committed to the approach. But they didn't have the energy to reach the runway, and by the time they realized that, it was too late to do anything about it. Now let's talk about visual illusions, because these play a huge role in approach accidents, especially in marginal weather. There are several well-known visual illusions that can cause pilots to fly approaches that are too low. One is the black hole approach I mentioned earlier. When you're flying at night or in conditions where you can't see the terrain clearly, the runway appears to be closer than it actually is. Your brain uses the size and shape of the runway to judge distance, but without surrounding visual references, those judgments are often wrong. You think you're on glide path, but you're actually low. By the time you realize it, you've already impacted terrain short of the runway. Another illusion is caused by upsloping terrain or an upsloping runway. If the terrain rises as you approach the runway, or if the runway itself slopes upward, it creates an optical illusion that makes you think you're higher than you actually are. Your brain expects the runway to be level, so when it sees a runway that appears to slope upward, it interprets that as meaning you're high on the approach. Your natural instinct is to descend to correct, but you're not actually high. You're on glide path or even low. When you descend to correct for the illusion, you go below the proper glide path and you end up short of the runway. Statesville Regional Airport has runway 28 sloping upward slightly from the approach end to the departure end. It's not a dramatic slope, but it's enough to create a visual illusion. If the crew was flying a visual approach, using the runway as their primary reference, that upslope could have made them think they were high when they were actually on glide path or low. The natural correction would be to descend, which would put them even lower. Add in the marginal weather, the low clouds, the reduced visibility, and the stress of the emergency, and it's easy to see how the crew could have ended up below a safe glide path without realizing it. There's also a phenomenon related to runway width. Narrow runways make you think you're higher than you actually are. Wide runways make you think you're lower. Statesville's runway 28 is 50 feet wide, which is narrower than the runways at major airports. If the crew was used to flying into airports with wider runways, the narrower runway at Statesville might have created an illusion that they were high, prompting them to descend when they should have maintained altitude. All of these visual illusions are well documented. They're taught in pilot training. Pilots are warned about them. But knowing about them intellectually doesn't always prevent them from affecting you in the moment. When you're in the cockpit, when you're tired, when you're stressed, when visibility is poor, your brain reverts to instinctive judgments based on what you see. And if what you see is creating an illusion, you'll fly to that illusion unless you have other references to correct it. This is where approach lighting systems and visual glide slope indicators like PAPI or VASI become so important. These systems give you objective references that aren't subject to illusion. A PAPI, or Precision Approach Path Indicator, shows you 4 lights. If you're on glide path, you see 2 white lights and 2 red lights. If you're high, you see more white lights. If you're low, you see more red lights. It's a simple, objective indication of your position relative to the proper glide path. But it only works if you can see it, if you're looking for it, and if you're close enough for it to be useful. Statesville Regional Airport does have a PAPI system for runway 28. If the crew was looking at it, if they could see it through the weather, it would have told them they were low. It would have shown them 4 red lights, indicating they were well below glide path. But here's the question. Were they looking at it? Could they see it? And if they could see it and it was showing 4 red, did they have the aircraft performance to correct? If the aircraft was already descending at a high rate, if the engine thrust was insufficient to arrest the descent, seeing the PAPI wouldn't have helped. They would have known they were low, but they wouldn't have been able to do anything about it. There's a saying in aviation, red over red, you're dead. It refers to the PAPI lights. If you see 4 red lights, you're dangerously low. You need to add power, arrest your descent, and get back on glide path immediately. But that saying assumes you have the aircraft performance to do that. If you don't, if your engines can't produce enough thrust, if your configuration is creating too much drag, then seeing 4 red lights is just a confirmation that you're about to crash. It doesn't give you the ability to prevent it. Let's talk about some historical accidents that are similar to the Biffle crash, because understanding the patterns can help us understand what happened here. One of the most well-known accidents involving an impact short of the runway was Asiana Airlines Flight 214 at San Francisco in 2013. That was a Boeing 777 that was too low and too slow on approach. The crew was hand-flying a visual approach and lost situational awareness about their speed and altitude. The aircraft's autothrottle was in a mode where it wasn't maintaining speed automatically. The aircraft got slower and slower, lower and lower. It struck the seawall at the approach end of the runway, breaking apart and catching fire. 3 people died and many more were injured. The NTSB determined that the probable cause was the crew's mismanagement of the approach and their failure to monitor airspeed. Another relevant accident was Delta Airlines Flight 191 at Dallas-Fort Worth in 1985. That was a Lockheed L-1011 that flew into a microburst on final approach. The wind shear from the microburst caused the aircraft to lose lift and descend rapidly. Despite the crew's attempts to recover, the aircraft struck the ground short of the runway, impacted a car on a highway, and crashed into water tanks. 137 people died. That accident led to major improvements in wind shear detection and avoidance systems, but it also highlighted how quickly an aircraft on approach can go from normal to catastrophic when energy is suddenly lost. Closer to the Biffle accident in terms of aircraft type and operation, there was the crash of a Cessna Citation in 2014 at Hanscom Field in Massachusetts. That aircraft crashed shortly after takeoff, but the investigation revealed issues with control lock that prevented the aircraft from climbing. The crew tried to return to the airport but crashed short of the runway. The similarities are that both involved citations, both involved attempts to return shortly after takeoff, and both ended with the aircraft impacting short of the runway. What all of these accidents have in common is energy management failure. The crews lost control of their energy state. They ended up low and slow without the performance to recover. And once you're in that situation, the outcome is almost inevitable. You're going to hit the ground before you reach the runway. The only variables are how far short you impact and whether anyone survives. In the Biffle crash, 1,800 feet short tells us the aircraft was very close to making it. If they'd had just a little more altitude, just a little more airspeed, just a little more thrust, they might have cleared the obstacles and reached the runway. But in aviation, close doesn't count. You either make it or you don't. And in this case, they didn't. They were 1,800 feet short, and that was enough to turn an emergency landing attempt into a fatal accident. Let's talk about what the NTSB will be examining when they analyze this aspect of the accident. They'll calculate the aircraft's energy state at various points during the approach. They'll determine what altitude and airspeed the aircraft had at specific distances from the runway. They'll compare that to what would be expected for a normal approach. They'll calculate the descent rate and determine whether it was within normal parameters or whether it was excessive. They'll examine the engine performance data to determine how much thrust was available. They'll look at the cockpit voice recorder to understand what the crew was seeing, what they were thinking, and what actions they were taking in those final moments. They'll also examine the terrain and obstacles. They'll create a detailed map of the approach path showing the elevation profile. They'll identify exactly what the aircraft struck and in what sequence. They'll determine whether there were any unusual terrain features or obstacles that contributed to the accident. And they'll look at the approach lighting system to determine whether it was functioning properly and whether it would have been visible to the crew in the weather conditions that existed. One of the key questions the NTSB will try to answer is whether the crew realized how low they were. Did they know they were below glide path? Were they trying to correct? Or did they think they were on the right path until the moment of impact? The cockpit voice recorder will answer those questions. It will capture the crew's words, their tone, their reactions. It will tell us whether there were call-outs like too low or sink rate or pull up. It will tell us whether they added power at the last moment trying to climb. It will tell us whether there was a moment of recognition that they weren't going to make it. From a human factors perspective, this accident raises questions about situational awareness and how it degrades in high-stress situations. The crew had been dealing with an emergency for about 10 minutes. That's a long time to maintain high cognitive function under stress. Fatigue, stress, and task saturation all degrade your ability to accurately assess your situation. You can be looking right at your altimeter, but not really seeing it. You can be looking at the runway, but not accurately judging your position relative to it. Your brain is working so hard on other tasks, on managing the emergency, on flying the aircraft, on communicating, that it doesn't have the capacity left over for fine detail situational awareness. That's when accidents happen. Not because the crew was incompetent or reckless, but because the human brain has limits, and those limits were exceeded. Here's something else that's important to understand. The crew wasn't trying to land short. They weren't being careless. They were trying to reach the runway. They were doing everything they knew how to do to keep the aircraft flying. But the aircraft's performance envelope had been exceeded. They were asking the aircraft to do something it couldn't do. And no amount of pilot skill or effort can overcome the laws of physics. If the aircraft doesn't have the energy to reach the runway, it's not going to reach the runway. It's that simple.